power series. Power series are special kinds of series. In power series, we're going to have a variable. We'll call it x, and there are going to be some constants, c sub k and a's. A power series about x equals 0 is a series, the sum as k goes from 0 to infinity of our c sub k's times x raised to the k. So c sub k is a constant, and then x raised to a power. A power series about x equals a is a sum as k goes from 0 to infinity of c sub k times x minus a raised to the k. That number a is called the center of the power series. So here, when we have a power series about x equals 0, the center is 0. And here, when we have a power series about x equals a is the center of the power series. And the c sub k's are called the coefficients of the power series. Let's look at some examples of power series. The first one is the series x to the k. Here you have that the center is 0 because it's x and there's no minus in here. And your c sub k's are always equal to 1. Another example is the sum of x to the k divided by k factorial. Again, our center is going to be a equals 0 because it's just x to the k. And our c sub k's are going to be 1 over k factorial. Another example is k factorial times x to the k. We have our center 0 and our c sub k's are k factorial. And another example is this one. Here you have x raised to the k, so our center is going to be 0, and then everything else is our c sub k. So the minus 1 to the k over 3 to the k times k plus 1. As a final example, here's a series whose center is not 0. Its series is its center is 5, so a is equal to 5. And then the coefficients are 1 over k squared. Here's some examples of series that are not power series. This is not a power series, 1 over x to the k, because it's not a constant times x raised to the k. It's a constant divided by x to the k. This is not a power series. We don't have x raised to a power. This one is not a power series as well. Here we have something raised to the power of x, but a power series has x raised to a power. And this is clearly not a power series. It doesn't have x raised to a power as well. Alright, so here's the question. For what values of x does a given power series converge? And that's what we want to know. Alright. So here's a nice little theorem that helps us out. It tells us that if we have a power series, exactly one of the following is true. So you don't need to go looking any further. Either the series converges only at the center, or the series converges absolutely for all x, or in our last case, the series converges absolutely for all x in some finite open interval a minus r to a plus r, so an interval centered at a, and diverges if x is outside of that interval. Now notice it doesn't include the endpoints here. At the endpoints, x equals a minus r and x equals a plus r, the series may converge, either absolutely or conditionally, or it might diverge. So in the case of the endpoints, you're going to have to check those separately. That capital R here is called the radius of convergence, and that interval is called the interval of convergence. That's where your power series converges for which values of x. Alright, so let's do an example. Let's find the interval of convergence and radius of convergence for the series x to the k. Well, this series is a geometric series with a equal to 1 and r equal to x. So we know that the series converges absolutely when the absolute value of x is less than 1, and we know that it diverges when the absolute value of x is greater than or equal to 1. So we have that the interval of convergence is from -1 to 1, from this right here, and that the radius of convergence is equal to 1. That's just, you take half of the width of this interval. Alright, also note that for this particular series, we said it's a geometric series, so that means we know what the sum is when r, or in this case, x, has an absolute value less than 1. We know that this series here is equal to the function 1 over 1 minus x. And that's really important, so keep that in mind. Write it down somewhere where you can look it up. Alright, here's another example. Let's find the interval of convergence and radius of convergence for this series, x to the k over k factorial. Now when we do these, you're going to end up with a 0 factorial in the denominator. 0 factorial is defined to be 1. Alright, so for this series, we're going to use the ratio test for absolute convergence. In fact, this is the test you're almost always going to use when you're testing a power series. We set up our row. Our row is equal to the limit of our k plus first term over our kth term. We set up the limit. We simplify this part right here by flipping the denominator. We simplify as much as we can. By now you should know that k factorial divided by k plus 1 factorial is 1 over k plus 1. Here we have x to the k plus 1 and x to the k, so they all go away but 1 power of x. And this limit, as x, remember that x is not changing here. It's k that's changing in our limit. So think of this as a constant. So this limit is going to be equal to 0. Since rho is less than 1, that tells us that the series converges absolutely for any x. Our rho didn't depend on the value of x. It worked for any. So that means that our interval of convergence is the set of all real numbers and that our radius is equal to infinity. Alright, this is important to notice. We just found out that this series right here converges for all x. So that tells me that the limit of x to the k over k factorial is equal to 0. So this is growing exponentially, but this is growing, let's say, factorially. And the factorially is going to win every time. Alright, so let's look at another example. Let's find the interval of convergence and radius of convergence for this series, k factorial times x to the k. Alright, so using, before we do that, let's consider the case where x is equal to 0. If we plug in x equals 0 into this series, then we end up that the series is equal to 0. So it definitely converges there. If x is not equal to 0, then we can go ahead and use the ratio test for absolute convergence. Setting up our row is the limit of our k plus first term divided by our kth term. Gives us this. We go ahead and simplify this expression to get that it's equal to the limit as k goes to infinity of k plus 1 times the absolute value of x. The absolute value of x is constant in this limit, so that limit is going to be equal to infinity. Since rho is equal to infinity, we know that the series diverges when x is not equal to 0. So we found that our interval of convergence is just the point 0, and that means that our radius of convergence is 0. Alright, in this example, let's find the interval of convergence and radius of convergence for this series. It's an alternating series. So, we're going to use the ratio test for absolute convergence. We get that rho is equal to the limit of our k plus first term divided by our kth term. We set up the limit. We simplify this limit by multiplying by the reciprocal of the denominator. And now once we do this, you can see that the 3 to the k and 3 to the k plus 1 are going to simplify down to 3. The x to the k plus 1 and the x to the k are going to simplify down to x. And then I'm left with k plus 1 up in the numerator. And over here, this becomes k plus 2. The x and the 3 are constants in this limit, so we can pull them outside of our limit sign. And notice we have to keep absolute values around the x. And now looking at this limit, this is a rational function where the degree of the numerator is the same as the degree of the denominator. So that limit's equal to the ratio of our leading coefficients. So that limit is equal to 1. So we find that rho is equal to the absolute value of x over 3. Alright, so now there are 3 cases we need to consider. The first case is where rho is less than 1. And when that happens, we know our series converges absolutely. The second case is when rho is greater than 1. And when that happens, we know the series diverges. And then the last case is when rho is equal to 1. When that happens, we need to look at each case in that situation individually to determine if it converges or diverges. Alright, so case 1 is when rho, which we said was the absolute value of x over 3, is less than 1. When this happens, we know that the absolute value of x is less than 3. So that means our series converges absolutely when the absolute value of x is less than 3. In our second case, rho is greater than 1. That happens when the absolute value of x is greater than 3, and that tells us that the series diverges when the absolute value of x is greater than 3. Now the last case is when rho is equal to 1. That happens when x is equal to plus or minus 3. We said in this case, we don't know if the series converges or diverges. So we're going to look at it when x is equal to 3 and when x is equal to negative 3. So first we look at when x is equal to 3. When x is equal to 3, my series becomes, I plug in 3 for x, I simplify it down as much as I can, and now this is a conditionally convergent alternating harmonic series. If you were to write out the first few terms, you'd see that. Now when x is equal to negative 3, the series becomes this. We plug in negative 3 for x. These two multiply together, give me negative 1 times negative 3 to the k, which is 3 to the k. My 3 to the k's cancel in my numerator and denominator here. And then going on here, I'm left with the sum of 1 over k plus 1. And that is a divergent harmonic series. So we've just found that our series converges absolutely when the absolute value of x is less than 3. We found that it converges conditionally when x is equal to 3. That's when it gave us the alternating harmonic series. And that it diverges when x is between negative 3 and 3, including negative 3. So when we go to answer our question, we would say that the interval of convergence is from minus 3 to 3, including the 3, because it converges there, and that our radius of convergence is half the width of this interval. Its width is 6, so the radius is 3. Here's another example. Let's find the interval of convergence and radius of convergence for this series. Again, we have an alternating series. This series doesn't quite look like a power series because it's x to the 2k, but it really is a power series. It's a power series where our c sub k's are going to be equal to either negative 1 raised to the k divided by 2 over k factorial when k is even, or our c sub k's are equal to 0 when k is odd. So it is a power series, it's just every other term is going to be 0. Alright, so again, looking at our series, we're going to use the ratio test for absolute convergence. Rho is going to be equal to this. We simplify the limit in here by flipping the denominator. I expand this out so it becomes 2k plus 2. On the bottom I get 2k plus 2 factorial. Now, taking this here, x to 2k plus 2, here's the 2k factorial. I can rewrite 2k plus 2 factorial as 2k plus 2 times 2k plus 1 times 2k factorial. and there's x to the 2k. My 2k factorials cancel out. Here, when I simplify this x to the 2k plus 2 divided by x to the 2k, that becomes x squared. X squared is a constant, so we can pull that outside of our limit sign. And now the limit that we're left with is a rational function. The degree of the denominator is greater than the degree of the numerator, so that limit is equal to 0. So we get that rho is equal to 0, which is less than 1. So that tells us that our series converges absolutely for any value of x. So in this example, we get that our interval of convergence is a set of all real numbers, and that our radius is infinity. All right, let's look at another example. Let's find the interval of convergence and radius of convergence for this series. Now look at this series. This time it's a power series, but it's not centered at 0 any longer. See how it has x minus 5, and that's raised to a power? 5 is going to be the center. All right, so again, we go back to our ratio test for absolute convergence. We figure out our formula for rho. We simplify it by flipping the denominator. We combine things as best we can and simplify what we can. This x minus 5 to the k plus 1 is going to simplify with the x minus 5 to the k to give us x minus 5 here. The x minus 5 is constant because it's k that's changing in our limit, so we pull that outside of our limit. Make sure you keep your absolute values on, and we end up with the limit of a rational function. That limit is going to be equal to the ratio of the leading coefficients because the degree of the numerator is the same as the degree of the denominator. So we get that that limit's equal to 1. So we get that rho is equal to the absolute value of x minus 5. All right, so now what we need to do is break it up into the 3 cases. In the first case, rho is going to be less than 1. Solving that inequality, that tells me that minus 1 is less than x minus 5 minus 1, which is less than 1. Adding 5 across tells me that 4 is going to be less than x, which is less than 6. So that tells me, since rho is less than 1 there, that my series converges absolutely on that interval. In our second case, that's when rho is greater than 1. Solving that, we get that happens when x is less than 4 or x is greater than 6. So we know that our series diverges when x is less than 4 or x is greater than 6. So our third case is when rho is equal to 1. That means we don't know if it converges or diverges, and we'll need to look at each case individually. Well, rho is equal to 1 when x minus 5 is plus or minus 1, or that says when x is equal to 6 or x is equal to 4. Now when x is equal to 6, the series becomes, I plug in 6 for x, that simplifies down to 1 over k squared. And that we know is a convergent p-series. When x is equal to 4, the series becomes, we plug in 4 where the x is, that gives us minus 1 to the k over k squared. Now, since we know that if I look at the absolute value of the terms and add them up, that's going to be equal to this series. We already said that this series is a convergent p-series. So that means that our series back here converges absolutely. So we've just found out that our series converges absolutely for any value of x between 4 and 6, including 4 and 6, and that it diverges otherwise. So here we would answer that the interval of convergence is from 4 to 6, including the endpoints, and that our radius of convergence is, you take the interval of convergence, determine its width, in this case which is 2, and divide it in half. So we get our radius is equal to 1.